Welcome back to AI Cost Optimization, the series where we cut your LLM bill one layer at a time. In the last 3 episodes, we tackled 3 powerful layer 2 techniques: sliding window to forget odd messages, summarization to compress history before it gets too long, and prompt compression to strip unnecessary words from the prompt itself. All 3 of those are about trimming what you already have: existing messages, existing context, existing words. But today, we are going after a completely different problem. What happens when your AI assistant needs to answer questions about a large body of knowledge, like a product manual, a legal document library, or your company's internal database? The naive solution is to dump everything into the prompt, and that is extremely expensive. The smart solution is RAG, Retrieval-Augmented Generation, the technique that lets your AI find exactly what it needs and send only that to the LLM. Let's break it down. Imagine you built a customer support chatbot. Your company has a 500-page product manual. Every time a customer asks a question, the naive approach sends the entire manual to the LLM as context. That could be around 50,000 input tokens for a single request. At roughly $3 per million input tokens, that may sound small at first, but costs add up quickly. A single request costs about 15 cents. Now imagine 1 million customer conversations every month. That becomes approximately $150,000 in monthly input costs. RAG, Retrieval-Augmented Generation, solves this problem with a simple idea. Instead of sending the entire manual, first find only the sections relevant to the user's question. For example, if the customer asks, "How do I reset my device to factory settings?" we don't need all 500 pages. We only need the few paragraphs that explain the reset process. So instead of sending 50,000 tokens, we might send only 500. That's a 100 times reduction in input tokens. And instead of spending about $150,000 per month, the cost drops to roughly $1,500. Smaller prompts, lower costs, faster responses, and often better accuracy. That's the power of RAG. RAG stands for Retrieval-Augmented Generation. The idea is elegant. Instead of giving the LLM all your knowledge upfront, you retrieve only the most relevant pieces and augment the prompt with just those pieces. The RAG pipeline has 2 phases. Phase 1, the indexing phase. This happens once, upfront, before any user ever asks a question. You take your documents, you split them into small chunks, think paragraphs or sections. Then you convert each chunk into a vector embedding, a numerical representation that captures the meaning of that text. Those embeddings are stored in a vector database. Phase 2, the query phase. This happens in real time when a user asks something. The user's question is also converted into an embedding. The system searches the vector database for the chunks that are most semantically similar to the question. Those top matching chunks are retrieved and combined with the original question to form the final prompt for the LLM. The LLM never sees the full document library. It only sees the question plus the most relevant 2 to 5 chunks. Precise, efficient, cheap. Let me give you a mental model that makes this click. Think of a university library. Thousands of books, millions of pages. If you needed to answer the question, what is the boiling point of water? Would you read every book in the library first? Of course not. You'd go to the index, find the relevant section, pull that one page, and read it. That is exactly what RAG does. The vector database is your index. The embedding search is the librarian, and the LLM is the reader. But it only gets handed the exact page it needs. No wasted tokens, no irrelevant context, no inflated cost. Let's put some real numbers on this. Imagine you're building a customer support chatbot. Behind that chatbot is a 500-page product manual. That's roughly 150,000 tokens of content. Now let's see what happens without RAG. Every time a customer asks a question, the entire manual gets sent to the LLM, all 150,000 tokens, plus the user's question. Let's say the question is about 50 tokens. That means every request sends around 150,050 input tokens. At Sonnet pricing of $3 per million input tokens, that costs about 45 cents for a single request. 45 cents may not sound expensive, but AI costs are all about scale. If your chatbot handles 1 million sessions every month, you're spending approximately $450,000 every single month just on input tokens. Now let's see the exact same scenario with RAG. Instead of sending the entire manual, RAG first searches for the most relevant information. Maybe it finds 3 useful chunks. Together, they contain about 600 tokens. Add the 50 token user question, and the total context becomes only 650 tokens. Not 150,000, just 650. At the same pricing, that costs less than 0.2 of a cent per request, around $0.00195. Now scale that to 1 million sessions per month. The monthly input cost drops from $450,000 to only $1,950. Compare those numbers. $450,000 versus $1,950. That's a 99.6% reduction in input token cost. And the best part? RAG doesn't just save money. Because the LLM receives focused and relevant information, it usually produces more accurate answers as well. Lower costs, better context, better answers. That's why RAG has become one of the most important patterns in modern AI applications.
Hello. This is the lab part. In this lab, we will show how the RAG implementation will save more tokens by inserting the most similar answers for the user query into the prompt instead of using all the documents in our prompt. Let's start. First, we make embedding. Use embedding models, or mini-LM. This for convert the text into vectors. After this, we create ChromaDB, vector database to save the embedding inside it. Then here, I make a collection. It's an object from Chroma with the name of knowledge base, and use the similarity method, here cosine. There are 2 other methods for L2, for Euclidean distance, and for IP for inner product. But the most common is cosine. This is sample document text, document 1 till 5. Then start to make embedding for this document, one by one in a for loop, and save this for the collection. Then I make the function call RAGAnswer. This function takes the user questions and top chunk, top most similar chunks for the user query, and I set it to 2. So first for user questions, okay, I make embedding, and after this I use query. And return the top chunks that equal 2 of the most similar for the user query, that already embedded in previous line. After this, I use the context block that have the chunks, the top similar chunks. This context block already used in the prompt, augmented prompt. Here I use it. So here I insert top similarity for the answer of the user query into the context, into the prompt, and followed by the user. And here I define the model, Sonnet, and send to him the whole augment prompt that contains a part of the RAG response. This is the idea of the RAG, how the RAG will save the tokens by inserting the most similar for the user query, instead of using the whole document. After this, I make running this demo. You can see the answer. These are the questions of the user. Here, he is the user ask 3 question. For every question, he returns the top similarity for the user query, And this is for number of token used here for the first question, and the second questions, and the similar for number of tokens here. If we make a cost comparison for with and without RAG, we find very good results. For without RAG, here I use in our prompt the whole document, okay, and the past whole document as a prompt to the models. So here is without RAG, very cost for around 453,150 per month, if we make assumption of 1 million session per month. And with RAD, now the cost became 4,950 per month. So you make a save in the cost around 98.9%. This is the idea of using the RAG in saving the tokens in our prompt. Let's bring this together. RAG is a layer 2 technique. Layer 2 is input control part. It controls what goes into the input you send to the LLM. Instead of injecting an entire knowledge base into every prompt, RAG retrieves only the most relevant chunks and sends only those. Three things make it work together. First, chunking. You split your documents into small, meaningful pieces. The smaller and more focused each chunk, the more precise the retrieval. Second, embeddings. You convert every chunk and every user question into a vector that represents its meaning. This is what makes semantic search possible. Third, vector search. You find the chunks most similar in meaning to the user's question, not just keyword matching, but semantic similarity. The result? Your LLM prompt goes from hundreds of thousands of tokens down to hundreds, without losing answer quality. And at scale, that difference is worth hundreds of thousands of dollars per month. Let's take a step back and see where we are in the series. We've now completed all 4 Layer 2 techniques. Episode 6, Sliding Window. Forget old messages when history grows too long. Episode 7, Summarize History. Compress old context before it's dropped. Episode 8, Prompt Compression. Strip unnecessary words from the prompt itself. Episode 9, RAG. Retrieve only what's relevant from large knowledge bases. 4 techniques, 4 different ways to reduce input tokens. Each one attacks a different source of token bloat, and they can be combined. Sliding window plus summarization plus RAG, all running in the same system, each one reducing costs from a different angle. Before we continue to the next episode, let's take a step back and look at the complete AI cost optimization roadmap. The journey is divided into 4 layers. Each layer attacks AI cost from a different angle. Layer 1 focuses on output control. The goal is simple: generate fewer tokens. We cover techniques like better prompt instructions and setting max tokens to prevent unnecessarily long responses. Layer 2 focuses on input control. Instead of sending large amounts of context to the model, we reduce the size of the prompt itself. This includes sliding window history, conversation summarization, prompt compression, and RAG. Together, layers 1 and 2 can often reduce token usage by more than 90%. And as you can see, we've already completed both of these layers. Next comes layer 3, call reduction. At this point, we're no longer optimizing individual requests. We're reducing the number of requests sent to the LLM in the first place. Techniques such as exact response caching, semantic caching, and rate limiting can dramatically reduce API calls and further cut costs. Finally, Layer 4 focuses on cost per token. Even after optimizing prompts and reducing calls, we can still lower costs by choosing the right model for the task. Techniques like model routing and batch APIs help achieve the same business outcome at a lower price. Notice the order of the roadmap. First, reduce output tokens, then reduce input tokens, then reduce the number of calls, and finally, reduce the cost of each token. When all four layers work together, the result is simple: lower AI costs, faster systems, better scalability, and production ready AI applications. So far, we've completed layers 1 and 2. In the next episodes, we'll start exploring layer 3 and learn how to eliminate unnecessary LLM calls altogether.